Welcome to This Explainer. Okay, today we are going to do something really fun. We are going to strip away all the sci-fi magic and the Hollywood myths surrounding artificial intelligence. I mean, forget about sentient robots taking over the world for a second. At its absolute core, machine learning is just a highly logical, highly mathematical process of pattern recognition. It's simply a system that learns from data to make predictions. And today we're going to break down the exact mechanics of how that actually happens, step by step. So this brings us to the ultimate question, right? The one sitting at the absolute center of all AI. How do machines actually learn without rules? Think about traditional computing for a minute. For decades, we had to explicitly program every single rule for a computer to follow. You know, if this happens, then do that. But machine learning completely flips the script. It operates without being explicitly programmed with every single rule. So how exactly does it pull that off? To answer that, let's look at a wonderfully simple analogy. Just imagine teaching a young child to recognize cats. You wouldn't hand a toddler a complex biology textbook defining what a feline is, right? No way. You just show them thousands of pictures of cats and maybe thousands of pictures of things that aren't cats. Over time, the child slowly picks up on the visual patterns, the shape of the ears, the eyes, the fur. And later, when you show them a completely brand new picture, the child can predict, yep, that's a cat. Well, machine learning models work exactly the same way. They just do it mathematically and at an unimaginably massive scale. Here is our roadmap for today, our machine learning pipeline, if you will. We're going to start with beyond the magic, then move into teaching the machine, before looking at fixing the mistakes. After that, we'll navigate around the memorization trap, and finally wrap up with ML in the real world. All right, part one, beyond the magic. To really wrap our heads around this, just imagine a student cramming for finals. Let's say our input is the hours studied, and the output is their final marks. You put in 2 hours of study time, maybe you get 40 marks. Bump it up to 5 hours, you're looking at 75 marks. Put in a solid 8 hours, and boom, you get an impressive 95. The machine's entire job is basically to find the hidden relationship between these two factors, just so it can accurately predict the score of a completely brand new student. Moving on to step 2, teaching the machine. Okay, so how does a machine actually sit down and study? Well, it all starts with something called features. These are the pieces of information or inputs given to the model. Think of features as the absolute key concepts our student has to learn. They can be literally anything, from age and salary to the temperature outside, the number of clicks on a website, or, like we just talked about, study hours. And the golden rule in machine learning is that the quality of these features heavily dictates the final prediction. I mean, if you give a student a terrible textbook, they're going to fail the test, right? The exact same thing happens if you feed bad features to a machine learning model. And this studying process, it happens in an exact repeating pipeline. First up, collect the data. Second, extract those crucial features we just mentioned. Third, the model analyzes the patterns. Fourth, it calculates where it made mistakes. And fifth, it adjusts itself to get better. It's this relentless iterative loop that literally only stops when the predictions finally get accurate. Let's actually demystify what's going on under the hood during that pattern analysis step. It sounds complex, but the model is really just trying to find mathematical relationships between inputs and outputs. For simpler models, it looks exactly like the math you probably learned back in high school, y equals mx plus b. You've got x, our input, like those study hours. The model is just trying to learn the absolute best value for m, the relationship, and b, the bias. Combine those and you get y, our prediction. So, going back to our exam example, the model simply learns the mathematical reality that more study hours directly equal higher marks. Which brings us to part 3, fixing the mistakes. Because, let's be real, learning is never smooth sailing, is it? What happens when our machine takes a practice test, applies all its fancy math, and just gets things completely wrong? Well, it relies on error calculation, and this is incredibly straightforward math. The model just compares the actual output to its predicted output. If the actual score was supposed to be 90, but our model guessed 85, we've got an error of 5. The model's ultimate goal, literally its entire reason for existing right now, is just to push that error all the way down to 0. To pull this off, the models use optimization algorithms, and the most common one has a seriously intimidating name, gradient descent. But honestly, don't let the jargon scare you. Gradient descent is simply a mathematical method that tweaks the model's parameters, step by step, to shrink that prediction error we just talked about. Think of it like a blindfolded hiker trying to climb down a mountain to find the lowest possible point in a valley. That lowest point, that represents the lowest possible error. The model just takes careful step after careful step until it finally reaches the bottom. Next up, part 4, the memorization trap. All right, training is over. Pencils down, we've reached the climax of the pipeline, the final exam. In the AI world, this phase is called inference or prediction. The model takes in brand new, unseen data, like a student studying for exactly 7 hours. It applies the mathematical patterns it spent all that time learning to produce an output, let's say predicting a score of 88 marks. This is the moment of truth. It's where we see if the machine actually learned anything from its training, or if it just managed to trick us. And this sets up the ultimate showdown in machine learning: generalization versus overfitting. Generalization, that's your successful student. They genuinely learned the core concepts and the underlying patterns, so they do perfectly well on a brand new, unseen test. Overfitting, on the other hand, is the student who fell right into a trap. They just memorize the answers to the practice tests. They might look incredibly smart during training, but the second you hand them a final exam with even slightly different questions, they completely fail. A good model has to generalize, a bad model overfits. Finally, part 5, ML in the real world. So, how does our very mathematical student actually graduate and apply these skills out in the real world? Well, different tasks require different majors or algorithms. If a model needs straight-line relationships, like figuring out the price of a house, it uses linear regression. If it needs to make choices, like if income is over 50K, they're likely to buy, it uses the if-else logic of decision trees. Now, for incredibly complex tasks like image recognition or running massive language models like ChatGPT, it uses neural networks that actually simulate biological neurons. And for maximum accuracy, it can even bundle a bunch of those decision trees together into what's called a random forest. And all of these different algorithms build into massive real-world applications that literally shape our daily lives. I mean, this exact math and pattern recognition is what powers your Netflix recommendations, predicting what movie you'll binge next based on your watch history. It's your spam detection, predicting if an email is junk based on its keywords. It's the literal brain inside self-driving cars, constantly predicting road lanes and dodging obstacles. It's even out there revolutionizing healthcare right now by predicting disease risk and patient outcomes. It's absolutely everywhere. When you really think about it, all of these miraculous, futuristic technologies are ultimately just the result of a machine meticulously adjusting parameters to minimize errors on a massive, massive scale. Which leaves us with a pretty fascinating thought to end on. If machine learning is at its core just mathematical pattern recognition, an endless loop of refining predictions, what complex human behavior will it decode next? Thank you so much for exploring the mechanics of prediction with me today. Stay curious, keep looking for those patterns, and I'll catch you in the next explainer.